So you had to copy to main memory for the GPU. Then you had to copy from host memory that's owned by the GPU to host memory that can be owned by the InfiniBand card. Then you can send it, and then the other side you had to do that extra copy. So they fixed that for certain vendors for certain operations. Otherwise, if you're writing MPI calls and you start getting errors, you pretty much have to turn off the RDMA function in the MPI library and go to direct sending. So Fermi, like I said, Fermi helps with some of these issues, but not all. Okay. Thank you very much.
Can you comment on, there's a slide in here that showed like speed ups, run on the CUDA and run on the CPU. Can you comment on like what kind of speed ups you get? I mean, is it sensitive to your system size, or whether you're running 80,000 atoms or 200,000 atoms or a million atoms?
So, yeah, so you want to have, I would say, at least 10,000 atoms per GPU is a good ratio. The speedups that we're seeing is that one GPU is roughly equivalent to 12 CPU cores. So that's, if that sounds like, well, okay, you get a factor of 13 speed up, but there's not perfect parallel scaling within the program. So you can run it fast with, one CPU, a quad-core CPU and a GPU, as you could with 4 quad-core CPUs. So there's that balance, because the parallelization issues are still there. And the faster you make the nodes, the more you tax the communication network between them. So you say at this point, there aren't GPU clusters that are as large as the CPU clusters. And part of the reason is this, well, A, it's new, and B, it's hard to scale things up that high if you're getting to sort of the scaling limits of the code. So one of the tricks with GPU is that for something where you're getting into, a small number of milliseconds per iteration, GPUs are great for letting you do the same performance with less hardware. But at that regime, GPUs aren't going to let you do, a simulation that is scaling, if you're running it as fast as you can, adding GPUs aren't going to let you run it faster. It'll just reduce your power budget, reduce your space budget, various other things.
Running separate simulations simultaneously.
Yeah.
That's
like
it sounds silly from what you're talking about, but it's really helpful.
Yeah.
Well, if you're bandwidth bound or latency bound on the InfiniBand, the GPU doesn't make any difference. It's kind of like if you're bandwidth bound on the GPU, an extra floating point operation is hardly noticeable.
Yeah. No, I said so. The best application is one that sits completely inside a single GPU.
Yep.
Because then you've got one memory space, you've got the highest bandwidth, memory latency. As soon as you're going for 2 GPUs even on the same host, you've got that PCI Express bus.
Yep.
And the InfiniBand card is not that much slower than the PCI Express bus when you start getting up to quad data rate. So it's a limitation.
In fact, the host, it's funny. Believe it or not, what ends up being a bottleneck first, especially with the older machines, is the memory bandwidth of the host machine. Even before the PCI Express bus, a lot of the older machines, the host itself, the CPU and the onboard memory on the host, is able to sustain only about 10 gigabytes a second. One GPU by itself doing a peak transfer rate between the host and the GPU will use 5.7 gigabytes a second. That means that one GPU just transferring data back and forth eats half of the entire bandwidth of the whole machine. And on those older machines, if you had a multi-core CPU, if it was trying to do anything, you're basically, it doesn't even have any, it doesn't have anything left. So that's an interesting thing. The nodes themselves are actually pretty weak compared to the GPUs. If you put 4 GPUs in that machine, you can guaranteeably not achieve peak transfer performance to all 4 of them at once because the host simply does not have the bandwidth.
But now it's in the range of 30-40 gigabytes second bandwidth, which is aggregate.
Yeah, so that's a theoretical number.
That's a stream number.
So here's what's funny. Yeah, but it's a theoretical number because so you can get under perfect circumstances something like 25. That's on the bleeding edge inhale, and that's the best they can do. If you get higher than 25, you're doing too small of a test because you're getting an artificial result because it's being cached. So you have to make sure you run a big test to verify you're not getting a cache. And then the other is for that test, if you run multiple stream copies, that's each CPU going to its own directly attached memory channel.
Right.
If you have multiple GPUs, they're attached to the system through PCI Express bus controller hubs of some sort. And so the difficulty is, even though you may have a 4-socket machine, where the 4 sockets, when you say 30 gigabytes a second, that's not one socket.
That's one socket, yeah. Right. So when you have multiple sockets, the
the bandwidth should scale. But what's tricky is that you may have fewer PCI Express hubs and so on than you have sockets. And so ultimately, they become the only path in and out of the memory system for the hosts. And again, this is another thing, non-uniform memory access machines. So every CPU has its own socket. They have their own memory attached memory system. If you're talking from one CPU to a particular GPU, because of the way this is architected, the CPUs don't necessarily have direct access to that PCI bus. They may have to talk through one of their peer CPUs. When you do that, you're consuming the bandwidth not only for your memory channel, but also your peer's memory channel, all the way to that PCI Express bus. And so if you have the wrong CPU talking to a particular GPU, it can actually exacerbate this situation where you're tying up some of the aggregate memory bandwidth of the whole machine, in a scenario where several of them are being chewed up rather than one.
Yeah, so when I say 30 or so, it's one socket, because those issues come in if you have multiple sockets, PCI Express coming. So is optrons any better because the hypertransport is better designed where you have direct attached to each socket, and so you don't have to go through multiple peers.
Same problem. Actually, that happens on Optron too. Exactly the same. Both QuickPath and Optron hypertransport have the same basic idea. They have a point-to-point link between CPU sockets. Each CPU has its own memory. If you want to talk to memory that's on another peer's controller, you have to talk through these point-to-point links. So anything that's not local ends up tying up these links, and you're competing for access both to memory and to devices like GPUs. And so that's an aspect of modern motherboard design that is maybe could use some revision in order to better support high bandwidth devices like InfiniBand and GPUs. Back in the old days when you only had one InfiniBand card and that was the only high bandwidth I/O device on the whole machine, it wasn't a big deal. But now if you have 2 or 4 GPUs, or let's say they're dual GPU boards, you could end up in a scenario where that machine just cannot push that much data over all these interconnects.
What about SLI then? I mean, why can't we get a SLI?
So SLI is a graphic-specific hardware feature. So what it does is it places the pixel bus for the output pixels in sort of a round-robin scheduler, and so each GPU draws half of the pixels or half of the frames, and they get output through a common signal connector. But really, they're not sharing anything else. So they're just sharing the results over a simple, very low-cost network that's practically no more complex than a USB. And it's fast enough for that sort of thing. And so they're inexpensive. They don't really have a full network. Of course, I've asked the very same question. I said, well, why don't, I've asked NVIDIA, what if you replace those SLI connectors with a real point-to-point network and then you could do memory transfers direct from one GPU to another. You could have kernels spanning multiple GPUs, things like this. But it ultimately boils down to cost and whether or not they would have any conceivable use for such a feature outside of high-performance computing. So that's the trick. Anytime you want to ask the GPU hardware guys for a new feature, you have to imagine how it would be used for video games, how it would be used for Google Earth or other sort of mainstream applications and not just what we do. And you'd have to imagine it costing on the order of a few dollars to implement in a commodity device in order for it to be appealing for the engineers to add that feature.
Well, they have the physics cards now, right? Physics
Not
stuff.
anymore.
They got rid of that.
Well, so NVIDIA bought Aegea, and now physics is CUDA. So they rewrote all the physics code so it just runs in CUDA.
So why not, I mean, if the physics is getting more complicated,
Yeah.
why not, I can see where this would be absolutely applicable still to that. Have one card do physics, have the other card do the graphics.
Well, they can do that now. They don't even need a wire for that. That's the thing. You have to come up with a reason why they should have a network between the two cards. And they don't need one to do what you're describing. They can do that now. So that's the trick. We have to be imaginative and come up with ways that this benefits a lot more people than just us.
So one other point you could comment, both of you, John and Kim, is you talked about the PCI Express being the limiting factor. So you have to amortize the cost of the transfer by enough work where that is not an issue, right? So when you design this, you have to think about maybe limiting the GPU work so that you limit the transfer from the host memory to the global GPU memory. So what kind of decisions have you made on that so that the PCI Express transfer is limited as much as possible?
Well, you definitely, when you think about moving more work to the GPU, you obviously pick the items that are most computationally dense first. So if you have, a lot of the examples we've shown that have these tremendous speedups are algorithms that either have quadratic time complexity or they were algorithms that have a small component that is significant time complexity, or if not time complexity, at least the absolute scale of the ratio of floating point operations versus memory references is much higher than 1 to 1. And so it is easy or easiest to move things that have a very large ratio like that to the GPU because you might be doing 100 times the arithmetic ultimately per, than the number of bytes or something like that, or some even larger number. And in much the same way you have to look for arithmetic-bound kernel design, you have to look in general at things that are arithmetic-bound because not only are you dealing with that global memory bandwidth once it's there, but you had to originally get it there. So, but the other thing is, if anything that's iterative, where you're going to go through the same data set many, many, many times, or a large component of your data set might have some reuse, those are good candidates for putting on a GPU. But if you had something that's effectively, like a good example, a GPU is not probably going to be any faster at reading encyclopedia text files from disk and counting the occurrences of the word the. It's because that is really something where the bandwidth is the dominant factor. The amount of arithmetic or logic that's being executed is trivial, and you can't really make it. It's going to be, disk bound or some other thing that will limit your performance. So putting that on the GPU doesn't make any sense.